Hi, everybody. Good morning. Good morning. Good morning. Good morning. I have been veritably frothing at the mouth for this machine learning, inference discovery, and anomaly detection session, and I hope you all have been too. We have a very exciting lineup for you today. Lots of interesting speakers, lots of interesting science to hear about, and let's get started. So the first things are, my name is Willow, my pronouns are they, them, and this is Sid.
My pronouns are he, him.
Excellent. And let's get started. So to begin with, a reminder of the code of conduct, that we are adhering to a code of conduct here at the conference. And if you have any questions about that or any concerns or like to bring unwanted attention to anyone, then you can reach out to these code of contact people. If you have COVID or if you have questions about COVID or you're feeling unwell, then there is an email to contact about that. Please be mindful of name tags, suggesting people's suggested contact levels. There's a lost and found at the RCW registration desk, and please be mindful of people's social battery. It is Thursday after all. And a reminder for when the session gets started. So first of all, we have a Slack session, which we will be using. You're more than welcome to put in questions and comments on the various speakers in there throughout the session. If you don't want to talk about them, if you're on Zoom, then please be muted if you're not speaking. And we're going to do our very, very best to make sure that all of you who speak in the room speak directly into a microphone. So make sure to say your name and maybe a fun fact, like where you're from and what you do. If you want, you don't have to. Probably not. This is probably wasting time. So, and also you can use the Zoom chat as well. All right. So today, this is our agenda. It's packed. So get ready. First, we have Guillermo talking for 10 minutes, and then we have various other speakers. We have a flash talk, and then we have another tutorial on doing science and machine learning on the Rubin Science platform. So without further ado, can Guillermo make their way to the stage? Excellent.
Hello, everyone. Thanks again for inviting me to give this talk. My name is Guillermo Cabrera Vives. I'm the PI of Alersi, and today I'm going to talk about some machine learning that we've been doing in Alersi. So first, you may know that Alersi is one of the community brokers, and we plan to do a lot of things, and we have been doing a lot of things during CDF, and we're applying all of the knowledge we gained with CDF for Rubin. But on this particular talk, I'm gonna speak about classification, features, and outliers detections. If you want to know more about the other things, I would be happy to talk about them later. So the talk is divided into two chapters. The first one is about classification, and we're going to talk about classic random forests, and we're going to talk about transformers. And after that, in chapter number 2, we're going to talk about autoencoder-based anomaly detection. And so I look forward to speak about all of these characters. So chapter number 1, classification. So the first classifier that we put in production in Alersi was a random forest created by Paula Sanchez-Saez. This was like 2020, something like that, maybe 2019, I don't remember. Sorry. And it was basically a random forest, which I guess most of you know. We calculated around 185 features from the light curves of the alerts that were coming from CDF. And Paula did a slight modification on the model, but it was basically that, a random forest, a balanced hierarchical random forest. This model was the state of the art in Alersi for real alert classification until 2023, I think. Okay, so we tried a lot of deep learning models, all that came up in the literature, and they didn't work on real data. Okay, so and this model is what we called handsome Squidward. Okay, that's the name the engineers gave it to him. I don't know why. All right, that's engineers. So in 2023, this guy over here, Nicolás Astorga, he was a former student from one of the members of Alerce. He said, I can build a transformer model. And we've been working for like 5 years trying to implement deep learning models into Alerce, and none of them worked because they didn't generalize to real alerts. So I said, no way, we're not doing that, okay? And he said, yes, I can do it. Okay, I told him, you have 2 weeks to show me that this works. And in 2 weeks, he got the model working, okay? And this is a transformer model, which he called AT-AT. And it's basically, it has 2 branches. One of them is for the light curves. So it's multimodal. It works with the light curves and also with tabular data. Tabular data such as context data in a table that goes with the alerts. And so he built a time series transformer and a tabular transformer, which is another way of doing a transformer. Raise your hands if you know what a transformer is. Okay, I can briefly explain it. It's basically a deep learning model that chooses where to pay attention in the data or where to pay attention in the representation of the data in order to make predictions. So in the time series transformer, he paid attention to the points in the light curve. In the quantile feature transformer, what he did is the model paid attention to features in order to make their decisions. And then the representations are concatenated, and then the model makes a prediction. Okay. So first lesson learned from me, for me, it's like I need to trust more my students. And this is what we call Mbappé. All right. So if we compare both of them on force photometry data from CDF, basically, they are very similar. Both of these are in production. Mbappé has a beta tag, which means that it's still not fully proven that it works. And a thing that happened is that for these models, we added new classes that we didn't have before. I'm going to talk a little bit about why we added these classes, and it has to do with anomaly detection, which is my next chapter. So then this guy, who you might have seen in the previous slide, he said, okay, but what if, this is Daniel Moreno, a former student of mine. He said, what if instead of using the light curve, I plot the light curve and I do a computer vision model on top of that to look at the images, right? And I was like, dude, no, that's never gonna work, right? No way, why would that work? If you have access to the light curve, it should work better than just looking at the images. And he said, oh, okay. And then next week he said, oh, by the way, I did this, I did it this weekend and it works better than the light curves. And so again, I didn't learn my lesson, so I should trust my students, right? And so he did this, and he basically used a vision transformer. It's the particular Swift version 2 transformer. And he was able to make it better on the light curves, only on the light curves without using the metadata than our previous model. So right, so this works. So we submitted the paper, and then he said, what if I do it in a multi-survey scenario? So we grab data from 2 surveys and try to see if this works. And again, it worked, right? So he created a multi-survey vision transformer, and it's super simple if you think about it. You just plot the light curves, and then you give the plot to the model, right? And so this paper was accepted at the ICML Machine Learning for Astronomy workshop before the other paper has been accepted. It's still under review. So this is like an evolution of a paper that hasn't been accepted yet. Oh, whatever. So chapter number 2, anomaly detection. So I'm going to talk a bit about autoencoder-based anomaly detection. So the idea is you have an image, let's say like this beautiful dog, and you create a latent representation of that. So you have a latent space where you have a representation, let's say a vector of that dog. And then what you try to do is to reconstruct the dog from the latent representation, okay? And if you can do that, then you can add something different that it's not on your training set, such as this. Do you know what this is? Raise your hand if you know what it is. Do you know how to make his sound? Okay, I'm not gonna push that. Okay, but anyways, so if you put that into the model, then as the model do not know that this kind of things, right? It's gonna be somewhere far away from the distribution of the things that the model knows, right? So if you think about it, we can do exactly the same thing with data with light curves, right? So we put the light curve, we train the model with all the light curves of the things we know, and then we put something that we don't know, and it's somewhere, thank you, somewhere far away from the distribution. So this is another former student, Manuel Perez Carrasco, and what he did was he used this idea, but he developed a new method in which if we know some classes of the objects, then he would create centroids for those classes and he would group them together, right? So when something new appears, then it will be far away from these clusters, okay? We tried this on data from CDF, and basically we tried a whole bunch of anomaly detection models for data from CDF, and his model outperformed most of the other models, not for all classes. So the way we did this is we hit one of the classes and we trained the model, and then we tried to find that class, right? And then we put this into production. And what happened was that on real data, this is what happens. So you can see the blue line here. Those are real outliers. And on the y-axis, you have the proportion of objects. They are sorted in terms of their anomaly score. So for transients, we got like 1, 2, 3, 4 outliers, real outliers. The way we did this is we put the model in production and we gave the 150 most with higher outlier score to the astronomers, and 12 astronomers checked them. So basically, it's really hard. It's really tough to work on this on real data. We found a TDE. We found a microlensing event. We found something that we didn't know what it was. But in principle, basically the TDE was discovered not by us as an anomaly, but by using spectra data from Hossein Sadeh et al. In 2020. So there's a team in Alerce that's dedicated to AGNs, and they had made huge discoveries, and they have been very popular, and they have appeared in the news, and they have become very famous. And the way they did this is not by using our anomaly score. Our anomaly score, no one uses it, okay? It's not really useful. The way they did it is by checking discrepancy between data sources. So here, for example, you have an AGN that was classified as a type 1 like variability by CDF with the CDF data, but spectroscopically was classified as a type 2. So there are a lot more examples there. We can talk about them later. But my point is that you cannot only work on anomaly detection with the light curves. You need data from different sources. And so this is a slide from one of Francisco's students. And it's basically like this. You need to know what different specialists say about the data that you have, and then make a decision based on that data. And that's it. Thank you.
Thank you very much, Guillermo. Would you like to take one question? Yeah, sure. So we have time for one question, if you'd like it. Yeah, Tatiana.
Hi. So I have two questions. Can I make two questions? So the first one is more a clarification about the vision transformer. I'm just confused. You plot the light curve and you use that plot as an image, and then, okay, that's interesting.
Yeah, exactly. That's what we did.
And I guess I have more questions about for later. Yeah. And but the second one is, so in this era of foundational models, whatever, maybe it's Alerce planning to have like the Alerce foundational model and then like derive every classification, whatever, from that model? Or
So we have built a bunch of foundational models. We built Astromer, which is one of maybe the first foundational model on data from, I think it was Ogle, Macho, and something else. But yeah, so the idea with about foundational models is that you create a lot of data. I mean, you have a lot of data. You use that data to train the model in a self-supervised manner so that it learns as much as it can from there. In practice, we have found that even though there are lots of foundational models, most of the times it's better just to feed your model directly to the data, most of the times. So for example, the vision transformer, that's a foundational model that we just grabbed out of the shelf, right? And so in that case, it worked. But if you're into very specific cases, then sometimes it's better to train your model from scratch. But maybe using the weights from the foundational model to fine tune the model, that those kind of things work.
Thank you very much. Let's please thank our speaker, Guillermo, once more.
Thank you.
Yeah. So, all right, next up we have Alex Razim. And I'll stop sharing because I believe Alex is online and I see her. Cool, Alex, take it away.
Hello, can you hear me?
Yes, we can hear you. I'll give you a 2-minute warning as a message on Zoom chat.
First, you have to allow me to share my screen.
Oh, wait, that's not okay.
Yeah.
Host tools. Yeah, can you try now? I think that should work.
Let me see. Yes, it should work. 1 second.
Right, yeah, take it away.
Yeah, you can see it.
Yes.
Okay. Many thanks. Hello, everyone. My name is Alex Razim from University of Nova Gorica. And I'm going to very quickly talk to you about how we are planning to search for anomalous variability with LSST data and other upcoming surveys in the next couple of years within the borders of my 2 years contract with SMASH program from European Union. So a very quick recap. In the last 10 years, we discovered that essentially most of the stars are variable in one or another sense. And we figured it out thanks to the high precision observations from the space. So TESS, Kepler, Ogle also, although it is not a space-based observatory, discovered that if you measure photometry with really high precision, everything is variable and everything is very curious because from this variability we can derive physical parameters, which previously was possible only with spectra. And also we discovered that there are many subtly anomalous types. So if originally we had more or less rough classifications, and now the number of different classes is rising, which you can notice from the classification schemes from our dear brokers who update these schemes regularly and include more and more interesting types. So if you look at the astroseismology data, for example, then you have anomalous classes all over the HR diagram. But with LSST, we are entering into a little bit different regime. So for the first time, we are going to have 6 bands, not observed simultaneously, but with pretty high cadence. I mean, obviously not like every 30 minutes, but still good. And we are going to have a very long baseline, which is fantastic because for the first time, we are going to have an opportunity to look for slow variability, which previously was undetected unless you stuck together multiple observations from multiple different surveys. And we already know that our knowledge of stellar evolution isn't perfect. So we keep finding anomalous cases, which are pretty hard to explain. Anomalous Cepheids, anomalous Lyra, stars which have metallicity values that are not very well agree with what we think about their informational channels. And the reason why I like to show this diagram from an annual astronomy review of 2015 is because on this diagram, you can see not only different types of variable stars with their different regimes indicated, but also this fantastic evolution formation channel of post-merger binary white dwarf that does multiple loops and changes its variability regimes back and forth. So a lot of these stages, they are actually pretty rapid. And this is another kind of anomalies that we are not, that we did not have a good tool to search for before, because we didn't have enough volumes of observations, of like regular observations, to catch these rapid transient anomalies, not transient events, but transient evolutionary stage. So for mostly historical reasons, we have mostly been using supervised machine learning for doing classification of objects that were previously classified by experts. So how we are going to search for previously unseen types of objects in this era when we have crazy amounts of data? So obvious answer is let's do unsupervised machine learning. But if many people consider still machine learning as magic, people who do not work with machine learning, then unsupervised machine learning is dark magic, because it is pretty hard to interpret unless you already have some labels that you can overplot over your outputs of your algorithms. And because these algorithms aren't very well adapted, aren't universally adapted to different types of data. So if we talk about random forest or neural networks, you can use something out of the box and it will give you reasonable result on almost any data that is well cleaned. With unsupervised machine learning, you will get some weird blobs of data, and good luck interpreting it unless you have something with high fidelity information, so like spectra. So obviously, we need to somehow push this forward, considering the upcoming volumes of data. And we need to try to adapt this kind of things to so many different classes. Because even if we look in the past history for the last like 10, 15 years, we will discover that actually we keep discovering new weird things. And they can be periodic, like some rare types of cepheids or chemically peculiar stars. They can be transient, like recently discovered ants, ambiguous nuclear transients, and rare types of TDs, which we expect to be observed and much more common with LSST. Or it can be stochastic objects, which mechanism we do not understand properly, and Voyager star is a great example of this. And what is funny is that most of these discoveries were made serendipitously. We didn't found them by looking specifically for anomalies. We found them by looking to other objects, and then suddenly an expert noticed something interesting. So first of all, as I already mentioned, so how we are going to do it? First of all, we are going to extensively use multiple surveys at once. So LSST alone isn't particularly good for finding variability that is not transient, because we won't have a cadence that is good enough for many variable stars in particular, which are my specific interest. But what we can do is we can try to map to cross-match in the shallow regime the high cadence surveys, such as TESS and Kepler with LSST. We can determine which areas of the color space anomalous objects occupy in 6-dimensional space provided with LSST. And then we can try to use these color cuts for determining areas of interest in the deep regime and study these objects in the deep regime with LSST. Plus, we are expecting that Roman space telescopes and Gaia epoch spectra are going to come out in the next 2 years. So kind of in synchrony with the first LSST data releases. So this is going to be an additional source of synergy that should be actively exploited. So this is what the MapLC project is dedicated, which started essentially a few months ago. So what I'm planning to do is to develop a more or less universal pipeline for studying different data sets in order to detect which types of objects can be anomalous or rare. Just to be clear, I do not plan to develop new classifiers because a lot of people are doing this on an excellent level. But what I'm trying to do is to use already existing feature sets. Yep. Oh, 7 minutes is up. I'm wrapping it up. Sorry. And it's not closing. So yes, already existing feature sets and already existing data sets in order to try to rediscover the previously found anomalous types of objects together with the data sets in which they were discovered. And in this way to practice this pipeline and figure out whether we can tailor it in order to be applied to the upcoming data from LSST and Roman. And this is three-pronged approach, which I plan to present, but since my time is up, I guess this is it. I apologize for over talking. Thank you.
Thank you very much, Alex. We have time for just one question in order to stay on rate. So are there any questions?
Any questions in the room? Any questions in Zoom or Slack?
I have one question for you, Alex. What do you see as kind of one of the biggest limitations, the biggest barriers to anomaly detection with LSST?
Cadence. Cadence isn't particularly good even for DP1, which has higher cadence than in most other cases. So for a lot of potentially anomalous types of objects, first few years until we get a long baseline, it won't be very easy. This is why collaboration with other surveys, synergy with other surveys is so important.
Great. Thank you very much, Alex. Another round
Thank
of applause,
you.
please.
Thank you.
All right, so it's me. Hello, everyone. My name is Sid, and I'm a PhD student at the University of Delaware. And today I will be telling you about how I'm planning to hunt for anomalies with distance metrics for LSST. And so it's here. Rubin is real. And we know that Rubin will be especially incredible for these 4 primary science goals. But like we saw in the previous 2 talks, like them, I'm also interested in Rubin's capability to discover entirely unobserved, never observed before astrophysical phenomena. And like Alex also mentioned, till now, throughout history, most of these discoveries have been made through serendipity. So someone being able to look at the data and see some differences. But now in the sea of new Rubin data, there is a real risk that we just miss out on these discoveries if we don't look at the data. I am trying to ensure that this doesn't happen by trying to plan for serendipity with machine learning. And so my goal is to find true novelties with Rubin LSST, where novelties, by novelties, I'm referring to astrophysical phenomena that have not been observed nor predicted. And we have heard this before as well, but this is in particular a difficult challenge because unlike other astrophysical problems, we don't know the kind of objects we're looking for. So we can't really plan around that like you would normally. And so our best approach is machine learning. And then if you wanted to do something like this, there's typically these 2 steps you would follow. Firstly, like any other kind of science case, it's really important, like your success really depends on how you represent your data. And as we saw from Guillermo, we know that we can represent our data by either extracting features, or we can also do some representation learning, so some deep learning to get some features from our data. And just to give you an example of what feature extraction is, essentially it means that if you have your data, so I have a light curve here, I can fit some models with some parameters and get those numbers, which I can then feed to my machine learning model. But the second step, once you have your features, is identifying anomalies from these feature representations. And this is what the rest of my talk will be focusing on. And so there are 3 really common methods which are used for this. Isolation forest, which we've already heard about in the previous few days, as well as local outlier factor, autoencoder reconstruction error, as well as what Guillermo spoke about. But I'm trying a new approach to this, where I'm using disclassify for anomalies, and I'll tell you more about it. And we expect that using multiple methods together might be the best way to hunt for these anomalies. And it has been shown that ensemble methods are highly effective for this. So methods that combine different approaches together. Last year, I worked on and released this classifier, which itself uses an ensemble of different distance metrics. So it uses these different distance metrics together for classification, and we showed that in this paper. But before I tell you about how I'm using it for anomalies, let me first tell you what a distance is. So a distance is a quantity that tells us how similar two objects are, which, as all of us know what a distance is. But we can visualize this by looking in this plot here. So the color represents the value of the distance from the center. So a darker color means a higher distance value. And we know that in case of Euclidean metric, this ends up looking like concentric circles. But we can mathematically formulate that a distance is any function that obeys these three axioms. And so we can swap out the Euclidean distance metric for many other distance metrics which obey these three axioms. And that's exactly what I did last year, and I talked about it at the previous Rubin workshop as well, where we tested a bunch of these distance metrics for classification. And I won't get too much into what we did for classification, but let me briefly touch upon how we're measuring distance. So the distance I'm talking about is the distance between features. Once you have your data, you have your features, you can calculate the distance between a test object to each of the classes you know. And you can measure that distance with different distance metrics. So depending on the kind of metric you're using, maybe it's Euclidean, maybe it's Canberra, maybe it's Lorentzian, the distance value changes. So it ends up squishing the space in some sense. And so we tested a bunch of these, 18 of these, and we found out that it worked really well, and we were able to classify very well, classify variable stars very well. But now I'm trying to expand this, and I'm using it for anomaly detection. And so my hypothesis for this is that an anomaly is a far away object, and it'll be far away from known classes for most distance metrics. And so if I have an unknown object, the black triangle here, and some known classes, I'm measuring the distance of this object to all my known classes and aggregating that so that I get a sense of how close I am to known classes. And for this, I'm taking the minimum. And then once I have this for one single distance metric, I'm repeating that for all the distance metrics I have, and then aggregating that as well with the mean. And then this final number is my anomaly score. And so to test this out, I was playing with Elastic, the perfect test bed for LSST. So Elastic consists of lots of many simulated light curves. And to think about this, like I did not want to inject a particular kind of anomaly, because then that would be biasing my sample in a way, right? So instead, I was playing with, my formulation for this was, I have some known classes, and I take a lot of other classes which are unseen and unknown to my algorithm, but these are still objects we sort of know. So this is sort of a good way to see if my anomaly detector can recover these unseen classes as anomalous. And so these are the classes I used in this example. And first, I started off by trying an isolation forest. And we found out that the isolation forest, all the top predictions were Cephids. And these are really interesting, really anomalous Cephids, because you can see that they have a really high brightness value, but they were still Cephids, not what I was looking for. If I use Disclassify, I saw that all of my top outliers were actually out of class unseen objects. And so objects like microlensing events, type 1a supernova 1991, like kilonovae, parent stability supernovae, superluminous supernovae, and ilots. And so a better way to maybe measure this is to see if we had a limited follow-up budget and we went after these anomalous sources, how many of the objects we follow up are actually out of class objects. And I ran this with the three methods I mentioned earlier. And what we see is that, especially for the first couple of hundred objects, the Disclassify, the distance metrics method, gives us anomalies that are out of class unseen objects. There are some challenges related to this, where the method is only good as the features we have. And as I talked about earlier, that is the first step before you apply this. So that is also something I'm working on. But if you want to learn more about that, please come to LSS Europe. I'll be talking about that. But yes, that's my summary. And I'll take any questions. Do join us at ISSCAD or TVS Anomalies if you're interested in any of this as well. Thank you.
Thank you very much, Sid. I think we just about have time for one question. Go ahead.
Thank you, great talk. One question, some distance metrics are effective, I guess, but the other might not, I guess. So there are two options. One is don't use that distance metrics, or we can adjust the weight for each metric. So which strategy did you take?
No, so here I was aggregating it by taking the average. I've been playing around with taking the median, et cetera, et cetera. But the point of the fact, like the matter is like based on our experiments from last year's, we found out that different distance metrics work better for different classes of objects. So necessarily, if you're doing anomaly detection, you don't know what kind of object it is. So just using all of them together and then getting a representation from that is seemingly, from our tests, that's the best we can do.
Thank you.
Thank you.
Thank you very much. Let's thank our speaker, Sid, once more.
All right, and I also get to introduce the next speaker now, which is Willow. So take it away. Not this. Sorry.
Oh, don't look at that. Don't look at that. Don't look at that. That was supposed to be a surprise. Okay. Hello, everybody. My name is Willow. My pronouns are they, them, and I'm here to talk to you about a brand new supernova classifier that uses spectroscopy or spectrum to classify supernovae. So first of all, there's one question that we need to get off right off the bat, which is the motivation for this. Why are we doing this? And here we have a lovely picture of a supernova outshining a galaxy. It just never gets old, does it? So spectroscopic classification is the most common way to identify most supernova subtypes. We've seen before that you obviously can do it photometrically, but spectroscopically is the way that Minkowski originally designed the spectroscopic classes, and so this is the most common way to identify them for most classes. We have this other problem, or this other fact, I suppose, which is that template matching, i.e. SNID, if you're familiar with SNID, it's a template matching method. That is the current most common way for identifying supernova. But template matching methods have a drawback that LSST is going to, well, it's going to take advantage of that drawback, essentially, is that template matching methods have a problem with scalability that machine learning methods don't. When you have a template matching method and you have to, if you're trying to type a supernova and you have to compare that supernova spectra to every single spectra in your template library, then that's going to take time as you enhance that library, and the libraries will be enhanced with LSST. So what did we do? Well, first of all, we needed a benchmark for classification, a benchmark for machine learning classification for developing a new classifier. And that's what we did. We took DASH, the deep learning for the automated spectral classification of supernovae and their hosts. Now, DASH is no longer maintained at the moment, but another version of DASH is in prep, so we're excited to see what happens there. But we retrained DASH as a benchmark for future machine learning classification models, in particular ours. And so our next step was to create our own, which we call ABCSN, the attention-based classifier for supernova spectra. We've actually just published this on the archive, today, I suppose. Thank you. And so let me talk about the data set that we're using to provide you a bit of context for what's going on here. So first of all, this type of map, by the way, is called a tree map. And this tree map shows the imbalance that is in basically all supernova spectral data sets. We have 3,700 spectra, which come from about 500 distinct supernovae, but 56% of those spectra are 1A normals, the cosmological supernova. And you can see, I believe offhand, it's about 70% are 1A, the main type 1As, and the rest are 1Bs, 1Cs, and type 2s. This is a really difficult problem that took up the majority of development time, I would say. A few of the ways that we get around this is data augmentation. I wish I could spend more time on this, but essentially we do various things. We inject noise to enhance, to enrich the representation of these fewer spectra in our data. We pretend that tellurics have been improperly removed from the spectra, and we play around with the redshift a little bit to simulate improper redshift corrections. Now, originally, we actually had a much larger data set. If you're familiar with supernova, you'd see these 10 supernova subtypes, and you'd say, that is not all of the supernova. And you're correct. And we removed several of them. And this kind of gets at the heart of the problem with spectral high signal to noise ratio spectral data sets, is that there aren't many of them for rare supernova subtypes. And so we've removed all of these. Additionally, I have 1A peculiars highlighted. We've suspected about partway through the development process, we suspected that 1A peculiars may be a sort of catch-all class for supernova that don't fit the bill for cosmology or anything else, although it may very well be a 1A supernova. And so we've removed that class as well. It was also poorly represented in the data set. And then one of the first things that we actually did is we decided to lower the spectroscopic resolution of all of our data. And in previous RCWs or Rubin CWs, we've demonstrated that this results in no loss in performance. And you can see on the right here, this is a type 1B spectra. At the top, we have it at the highest resolution, the resolution that we source our data from. At R equals 100, this is what the data looks like. And this is actually what we trained all of our data on. What we retrained Dash on as well, and at R equals 25, which is essentially the limit for the lowest spectroscopic resolution that is still worthwhile doing machine learning classification with. There's one more thing that we did, which we find really exciting, which is what we call pre-training. We take a spectrum here. I don't remember what kind of spectrum this is, but we take a spectrum. And before we train our model, what we do is we randomly select 15% of the spectrum and we mask it. We set it to 0. And so in this case, it was these two big features, or perhaps one feature here. And what we do is we train part of our model, and I'll show you the details of the model shortly, but we train part of that model just to recreate the original spectra based off of the masked spectra. And what I'm showing you now in red is the performance on this one particular spectra of it recreating that. And I find this particularly exciting because look at that, this entire feature, which was completely masked from the model, is completely recreated. And so what we do, we have this grand model here, and what we do is we use that information and inject it into the architecture. So this is a very complicated architecture diagram of ABCSN, and I'm just going to walk through here. We have an embedding. This takes our one-dimensional spectra, which is just fluxes versus wavelength. It brings it to a higher dimension. We have positional encoding. When transformer neural networks were first introduced by Vaswani et al. 2017, this was something that was identified that was really important. So we make sure to have that. The encoder blocks and the pre-trained weights. The encoder blocks, this is taken directly from the original transformer neural network, and that is the source of all of our large language models today. And you see I've highlighted here on the right, this is actually the pre-training model, and we copy those weights over to the model as we train. And then finally, we have the classification head. This is where, hopefully after the representation of the spectra has been learned within the encoder blocks, then the classification head can perform the spectroscopic classification. And so this is our results. And it's a very complicated confusion matrix. And I really want to bring your attention to just the top left here. So in blue, what we're showing are correct classifications. So this says true label on the vertical axis and predicted label on the horizontal axis. And so this is saying 925 of 1A normals were correctly identified as 1A normals. Everything on the off diagonal are incorrect classifications and are shown in red. And this is good. You can come back and look at this if you want to, but really we want to compare to Dash. So we're taking a look at the completeness and purity, or the recall and precision of our model, and comparing that to Dash. The first thing that cosmologists will be happy to see is that we do improve upon the purity of supernova 1A normals, which is very important for cosmology. We also drastically improve about 25 percentage points in the completeness of supernova 1A normal. That is, we're finding more of them. And then lastly, for non-1A supernova, we also have greater completeness, which is useful because these are our least numerous classes. Now, thank you very much for listening. There's some room for improvement, of course. We suspect some mislabeled spectra from SNID, especially in these least numerous classes, and we just need more spectra in general. A paper is out on the archive today. You can find it at this bit.ly link or at this QR code, and you can download our code right now. The model is on Zenodo, and there is a tutorial to get started classifying with ABSN. This is my gay cat, Orion. Thank you very much for listening.
Thank you, Willow. We have time for a question or two, if anyone has any. It was a comment on the cat, so great orange cat.
So do you know how your model or Dash compared to this template matching, like purity completeness?
So we don't really have a way to compare our methods to SNID, the original template matching method, because that is what we are assuming is true. That's where we get our labels from. In the future, we would like to be able to do that, though, definitely.
So for the augmentations, you talk about adding noise to that it's a way to enhance the like misrepresented classes. So the question is like, I think there's like a trade-off. So you can have like balanced classes, but then you know that one of the classes is not as good as the other one.
Yeah.
So how you like, I don't know.
How do you deal with the fact that when you augment your data set and you know that some of your classes aren't going to be as information rich? Well, you might cry a little bit, but ultimately that's, I think, a sacrifice that you have to make because the bias that imbalance will impose upon your model can be so significant that it is worth accepting, yep, some of these classes in the end won't have as good a performance as others because the information content is not as diverse. And there's not much you can do about that. Thank you.
All right. Thank you, Willow. It's Somaya first. All right. So next up we have Somaya, who will be telling us about lens quasars. All right.
Hi, everyone. I'm Samaya Kakbash. I'm an LSSD Catalyst Fellow at Rutgers, and I'm going to talk about this AI model that we have made to generate magnification maps for lens quasars and hopefully supernovae. So to tell you first about what the scientific question is, what is the challenge and why we're trying to solve it this way. Let's look at this image. We can see a lens quasar with 4 images around the lensing galaxy in the middle. And each of those images are arriving at a different part of the lensing galaxy, and therefore their light is going through a different distribution of compact objects in a smooth dark matter. And we can sort of like assume a distribution of compact objects in smooth dark matter, as you can see on the right, within that like a square on the lensing galaxy. And each of those images will be also lensed by, affected by the gravitational field of the microlensers. And as a result, if you look at the light curves of each of these images, like within a long period of time, we can see variability that is the same for each of the images, but also variability that is different. So that there's like the intrinsic variability of the quasar that is the same, and the microlensing variability that is different because they're going through different distributions of stars and smooth dark matter. But why do we care about the microlensing here? Because we can learn about the quasar structure. We can better measure time delays. We can learn about lens galaxy mass distributions. But the problem is, in order to have an understanding of this microlensing variability, we need something called a magnification map, which is basically a theoretical map that tells us what is the overall gravitational effect of the distribution of compact object and smooth dark matter within that square on the lensing galaxy. And it's going to be different at different parts of the lensing galaxy. And we can generate such magnification map assuming some parameters of the lensing galaxy on the left side. I will go back to that later. But the problem is that in order to get a good modeling of the macro lensing variability, we need to look at as many as these magnification maps in order to have some sort of constraint on the parameters of the lensing galaxy. And we also need to look at different trajectories of the source within this part of the sky on the lensing galaxy to find a better match to the model that we're looking for. And this is very computationally expensive because these magnification maps are computationally expensive to generate. So the idea was to basically build a model that can enhance the generation of magnification maps and help us better constrain the parameters of the lensing galaxy and also other parameters as well, especially with having LSSD, which will help us find like an order of magnitude more of these events. So we started by building an autoencoder trained on pre-computed magnification maps called Gerlach maps. These are made by Yorgos Vernardes. And so our paper was published earlier this year, and we showed that with this autoencoder, we're able to basically reconstruct these maps from a much lower dimension called the latent space representation. And we also showed that the maps that this autoencoder generates are reliable. We showed that these can be used for doing science. But we also developed some metrics to show if we have a magnification map, can it be physically a valid magnification map? Because in the next step, if we generate a new map, there's no way to go theoretically from the map back to the physical parameters. So we need to have a specific metrics that can tell us if this magnification map is valid. So in the next stage, we have been working on basically adding another model here that can take in the parameters of the lensing galaxy and generate examples of the latent space representation. And that is going through the decoder of the autoencoder to generate new maps. It turned out it's not as easy as we thought. And testing so many different networks show that this is a way more complicated problem. And so to repeat it again, what we wanted to do, I'm here like even simplifying that to get a better understanding of what we actually need. So on top, you can see an example of like a distribution of compact objects as an input to the model, plus two parameters on the bottom, kappa and gamma, which are describing that distribution. So kappa is telling us the total mass density, gamma is telling us the shear due to external mass. And that is supposed to generate, help us generate a latent space that goes into the decoder and gives us the map. It turns out the contrastive learning is helping us achieving that goal, is giving us a path forward. What contrastive learning does is that in cases where when you have inputs that are, the inputs have mutual information, but are in different formats, the contrastive learning will create an embedding, a representation of the data by trying to distinguish between similarities and dissimilarities of each pair of basically inputs in your data set. So here, basically, we're creating a representation of each of these types of input, the distribution, and the physical parameters. And the contrastive loss here is basically improving that representation for us and make sure that the model can understand the similarities between like each pair of kappa gamma and the corresponding distribution that we're giving to it. So the next step is now we need to choose the right training parameters, because that turns out to be significantly changing the training process. So here you can see on the x-axis, you can see like a bunch of models that I have trained And the differences between them is that the training parameters are different. And on the y-axis is the metric that I showed you before that we generate to basically assess the results of the network. And we can see all these ups and downs. So, so what we're doing is basically we're using these metrics and using the contrastive learning to basically try to find our path forward, trying to find like the best sort of training parameters and hopefully achieve the model that is achieving the satisfactory metric values compared to the what the autoencoder can really create at its best. With that, I end up. Thank you so much.
Thank you so much, Samaya. We have time for just one question. Just one, Tatiana. Any questions? Yes.
It's Phil Marshall here. Really nice application of contrastive learning to sharpen it up. I wonder, can you say something about the pros and cons of modeling the magnification map as opposed to the light curve directly?
Well, yeah, that's a good point. We are like for like another project, we are also like working on the light curves, trying to like find out if like we can actually like bypass the magnification maps and like go directly to the light curves. I don't have an answer for that question yet, but that's something I'm very curious to find out too, because I personally believe that to sort of like go through the maps will give us more information to be better constraining the physical parameters of the lending galaxy, but I still can't prove it. I'll have to try both ways.
Great, thank you.
Thank you very much. Let's thank Samaya once again, please.
All right, next we have Peter.
Hi, good morning. My name is Peter Veres. I'm from Harvard Smithsonian Center for Astrophysics, Minor Planet Center. And here I present our work on machine learning and how we can help in identifying interstellar objects. And this work was done with Richard Cloty, who is also here with me, and he will be happy to also answer your questions about machine learning. So interstellar objects are obviously one of the most interesting objects recently discovered flying through our solar system. And the latest one, 3I Atlas, was only discovered really this year. And those objects are not bound to the sun. So you can see an example of the solar system here. 3I Atlas is really only flying through the solar system pretty fast. So it's it's the most eccentric interstellar objects discovered so far with eccentricity of 6.2. And even though there have been papers predicting that Rubin Observatory is going to discover several interstellar objects, the papers mostly mention objects being detected. And there is a huge difference between discovery and detection. Basically, can you link them together? Can you distinguish them from the, let's say, bound object to the sun? So this is what we have done in our study here, and we used the simulated data from the DP03 synthetic model that used the solar system objects in two data sets. One is simulated in 1 year of the full LSST operation. One is a 10-year data set. And this data set contains simulation of almost 6 million synthetic orbits of the solar system. Of course, most of them were in the main belt, that's the background population, and about 12,000 orbits of simulated interstellar objects with different sizes ranging from approximately 100 meters to 1 kilometers in size. And basically, we pretended that we had tracklets on every single night, tracklet meaning at least 2 detections of the same object in the dataset. So we didn't try to link detections together into tracklets. We just pretended all those 2 or more detections of the same object per night are tracklets. So in our work, we obviously had a very unbalanced set, which is not very friendly for the machine learning because ISOs only represent a very tiny fraction of the simulated data. So obviously we needed more ISOs. So we created a pseudo similar survey, basically taking all the 12,000 tracklets that are in the simulation and basically recreated those tracklets in the 10 years of the survey data. So we kind of doubled the number of detections of ISOs we had. So at the end, we had many more ISO tracklets in our simulated data set. So what we actually studied, we didn't study the images, we studied the motion vectors of those tracklets, and actually two flavors of motion. So one data you obviously have, one piece of data is the observables. You have right ascension, declination. We had the orb type of every single object, so we knew whether an object is an ISO or not. And then we derived additional values like position of the object with respect to the opposition, what is its rate of motion, what is its angle of motion, the position angle. And we also use so-called digest2 values. Those are quasi-probabilistic scores for an object belonging to any orbital category. Like, let's say, what is the probability of an object of being an NEO, a main belter, or Hungaria, or Jupiter Trojan family, or Trojan. So we use this digest2 score, and we kind of divided our population of tracklets into the training and testing set and the validation data set. So the training testing 80 to 20. And we also studied if all these features are equally important or there is a difference. So the plot here shows that some features are more important than the others, obviously. So we only use the ones that are significantly important in distinguishing ISOs from non-ISO tracklets. So we used four different machine learning models. They have their advantages and disadvantages, like stochastic gradient descent, SGD, random forest gradient boosting machine, and neural network. So these are the four machine learning techniques we used to distinguish ISOs from non-ISOs. So obviously at the end, when we applied our methods on our tracklets, we kind of tried to look at the confusion matrices to try to distinguish which are better and which are not. So basically in the confusion matrix, you have the number of false positives, true negatives, etc., etc. So we are basically looking at the numbers circled in the red circles here. So, and try to figure out which model is the best. So among these fours, it seems like the GBM is giving us the smallest number of false positives. And at the end, it seems like our work is showing pretty high accuracy and precision. So we are talking about more than 99%, which is very promising. So that's pretty good results on the simulated data. But of course, we understand the real data are usually very different from the simulations. So in addition to just a large set of data we tried and tested on, we also looked at the three distinct nights from the simulations and tried to simulate how the realistic LSST survey looks like. So let's say we took three random nights that represented nights that were pretty busy in a sense. So we were looking relatively close to the ecliptic. And one night had basically 0 ISOs in it. So that's a typical night from the LSST, right? So usually you don't expect to see ISO on every single night. The second night we tested had 13 ISOs. So that's, I would say, unrealistically high expectation, but it's a good sample for a test. And third night had exactly 1 ISO. So this is a probably ideal perfect night. And in here you see we have true negatives in accounts of like 20,000. And basically the column here, true positive, tells you for different four models how many ISOs we found. So for the first night, zeros. So there was no ISO in the data, no ISO found with our model. That's great. And we only had like between 19 up to 66 false positives. So again, GBM works the best. The second night, we have from all of them identified up to 2. Again, GBM is the best. And the last night with 1 ISO, also most models found that single ISO and had from a few to like hundreds of false positives. So the conclusion is the GBM, maybe random forests are most promising. So if we have like, let's say 20,000 tracklets of real objects per night, we could find an ISO if it is in the field for the cost of having not too many false positives. But of course, obviously we need to apply our models on the real data, which we are trying right now. And it depends on how many tracklets there are at the end in the data sample. And this work has been published. So fingers crossed, and maybe we can help the linkers in near future to link ISOs from much smaller sample than running the linking on, let's say, on thousands or 100,000 of tracklets. We can provide probably much smaller sample to search for ISOs. Thank you.
Thank you very much. Are there any questions? We have time for 1 or 2 questions.
Thank you. Great talk. You in your features you used, I presume, for your GBM, I noticed that there were features like RA and deck, and I'm not sure about all the other features,
Yes.
but do you think that might be biasing your data set in some way where you might not want it to use the raw values, or even if you want to use a location, which I presume is important, maybe there's a better way to represent that rather than just the RA and deck? And have you thought about that?
So basically, at the beginning, we didn't know which features are actually important or not. So this was more about discovering which are not. So basically, all the features you see are mentioning in the table above. So the feature you can kind of distribute either like direct observables or like array decks, or derived values like the rate of motion or the digest2 scores. So at the beginning, we had no idea. So at the beginning, we wanted to only use the digest2 scores, not the observables. But then we were, let's use everything we had to have some results. So that was the reason we actually looked into the features at the first place.
Thank you very much. Let's thank Peter again. So next we have Rodiat giving a flash talk for her poster, which you can find out there right now.
Hello, my name is Rodiat Ainde. I'm a research associate with the University of Delaware, and my work has been on applying foundation models to for object segmentation for astrophysical images. And these are two separate use cases for foundational models for object segmentation. And on the left is an image of of a galaxy. This is UGC 7513. And with zero-shot learning, meaning you're not retraining your whole model, the bottom two right images, you can see that the foundational model is able to provide like a very an obvious good segmentation for this for the galaxy. And then the two plots right beside it show that it also provides good information about like the area and the ellipticity of these galaxies that we're trying to see how the segment anything model can properly like segment the galaxies in these images. And then on the right is an image of a light echo, and I don't know if you know what a light echo is throughout the previous talks throughout this conference, but they're the reflections of supernovae on interstellar dust. And if you look at the top right of the image, top left rather, you can see that there are two very faint portions of the image which are light echoes, and we can see from the remaining two images on the right that the foundational model is as successfully been able to like identify these parts as light echoes as being different from like the background of the image. And so yeah, the conclusion is foundational models can save computational resources because you're not retraining your whole model, because that's expensive and not everybody has the computational resources or the money to be able to do that kind of retraining. And then isolating neural networks and fine-tuning is an effective way to also save computational resources. And you can, thank you, Willow. You can come to my poster to learn more. And my poster has also been posted on the community website. So if you would also like to view it there, that's also possible. Thank you.
Thank you very much, Rhodia. And please go see that poster. Light echoes are really difficult to detect. Now I'd like to invite Andres to come up and give a tutorial, along with Sid, I believe, on how to do machine learning with the Rubin Science Platform.
Thank you, Willow. Actually, we'll be Sid giving the tutorial because he did all the hard work. So I'm going to be talking about a little bit of logistics and bureaucracy. I'll try to go fast over this because I want to really have time for the tutorial. My name is Andres Plazas Malagon. I work as Slack at Kaipak, but I'm also part of the community science team, which is the Rubin team that is here to support the users, to support you to make the best out of the LSST. We have expertise in all the science areas of the survey, and my own background is in observational cosmology, but of course we have experts in other areas as well. In particular, one of our experts in artificial intelligence and machine learning is Brian North from Fermilab, which I believe is connected, so in case we have questions. So I wanted to remind you a little bit about the RSP. I hope everyone here has an account, but if not, that's fine. If you have data rights, please go to rsp.lsst.io to get an account to this platform, which is a set of integrated web services in order to apply to access the LSST data. So we have three aspects in the Rubin Science platform, but in particular today we're going to be doing a demonstration with the notebook aspect. The notebook aspect, here are some specifications of the capabilities that it has, of the storage that you're going to find in there, but you can do stuff like defining users groups, you can install your own packages, you can run Python scripts and even access the command line. Something also very cool that we have developed in the community science team is a series of tutorials for you to explore at your own pace. And once you get access to this aspect of the RSP, you can just go to this tab and then you will see all the tutorials. I also wanted to point out that this roadmap, which also gives you a more example of the type of scope and the things that you can do with the RSP. And we are in data preview 1. We want to hear from the community if you want to do machine learning anomaly detection with the RSP. We want you to tell us like, I can't do this, I cannot do that, I would like to see this and that, GPUs, etc. We don't have GPUs at the RSP, but there are alternatives, so talk to us. And the way of talking to us officially is going to community.lsst.org, go to the support category. I guarantee you that we will give you an answer, or we'll find the expert to find the answer. And think that if you have a question about the RSP, probably somebody else will have it, or anything about Rubin. So it's great to use this as a community tool. So getting a little bit into the topic of the session. So I want you to focus on DP1 on Sky Data, but I wanted to mention that we have also developed tutorials related to the topic with the simulations that we had so far. This is data preview 0. We have a cosmology simulation and a solar system simulation. In particular, I wanted to point out to this introduction to AI tutorial by Brian North. It's a great tutorial. I gave it to one of my summer students this summer, and it was perfect. Then a former member of our team, Ryan Lau, also made an anomaly detection tutorial. Again, this is with the previous simulations, but I wanted to point it out, and because you can also easily access them via the RSP. There's also, this is one example of one paper of the community, somebody using the solar system simulations to use anomaly detection with that, but I'm pretty sure there are other examples out there. So very briefly, I wanted to tell you about the data products that we're going to talk about in this tutorial. So we're basically using the difference image analysis data products, in which we have a science image, we have a template that is built from if you have a certain amount of visits, you take the third subset that has the best scene, and then you build that template, then you construct a difference image. And then also, we can also get light curves from different transients and objects that of interest. But in more detail, so we do the PSF machine, PSF matching to construct this template coad. It's the Allard and Lupton algorithm is done. Then we subtract for every single input visit image, we subtract that template. We get what is called a difference image. And then in those difference images, we do detections of sources with a signal to noise ratio greater than 1. So that's going to give us these DIA sources. Then we do, in all the visits that we have these difference images, we do associations of sources within 1 or seconds, and then we're going to have the DIA objects. So these are some of the data products that are of relevance in this case. But then we also do force photometry in all the difference images and visit images at the locations of the DIA objects. And then that will allow us to get light curves in another data product that is called the force source on DIA object. So this is just a visual example of like a deep coad, and then on the right side hand panel of the template coad with the best seen images. I might skip this, just gonna put them for reference, but these are some of the specifications of the data products that I just mentioned in terms of columns and the key columns and number of rows. In particular for the DIA source table, and the fourth source on the IA object table. We do have one tutorial per data product again in the RSP, so you can do it at your own pace. Then again, this is for reference of some of the tutorials that might be relevant for this session. And this is a screenshot of what I was just talking about. You just go to the tutorial, that tab, you'll find the DP1 tutorials, but also you have the DP0 tutorials as well. Just very easy to access. So now we're gonna do demo time. There is a report prepared by Sid, and you can run the notebooks at the cloud. And yeah, thank you. Are you gonna run here?
Okay. I'm gonna share my screen with my laptop on here. That should work fine. So thank you, Andres. And I know that Andres said that I did the hard work. That is a lie. It's these incredible people of the Rubin community science team who have been putting out these wonderful tutorials. So they have been doing real hard work, and a big shout out to them because the tutorials are amazing. They're easy to follow through, and I'm having a blast exploring DP1. So maybe a round of applause for them. Cool. I believe you can see my screen. So yeah, my tutorial is not up on the Rubin Sense platform yet, but I have created this GitHub repository, which if you want to follow along, I'm also putting it in the chat if someone wants a link online. But there's also a tiny URL which Andres shared earlier, which is this. So feel free to follow along if you want. If not, that's fine too. I'll just give you a quick demo. And good news is that I did prepare a short tutorial, so we'll still be on time for lunch. Do not worry. So just to, for people who might not have used the Rubin Sense platform, it is this incredible URL, data.lsst.cloud. I love it. There's multiple aspects to it, which Andres pointed out earlier. We'll be using the notebooks, and you do need data rights for these. So you will need to log in. I will log in without, let's turn off my screen. Oh, I don't need to authenticate because they remember it's me. Okay, I'll share my screen again. So yeah, once you're logged in, you'll be shown a list of servers you can choose from. Let's go with the recommended one, and it shouldn't take more than like a minute. I haven't ever done this live, so maybe if there's hundreds of us, okay, no, we're good. So, yeah, the really good part of the Rubin Science portal, like the platform, is it's very easy to pip install packages. And so I will be, a lot of my tutorial is based on what Andres, the links he shared earlier. So tutorials that have been made earlier by Ryan and Brian and a lot of other people. And so I've just adapted that for DP1. And first I'll be showing you how to run an isolation forest on light curves from DP1. And then because I'm giving this tutorial, I'm also showing you how to run my method on it. So this is the Rubin Science platform, and these are the tutorials. If you want to access them, there's DP 0.2, 0.3, and there's tutorials on AI as well as Anomaly. So you can take a look at those. But the first thing I want you to do is, nope. Yes, so first thing we want to do is git clone this repository. So I have some instructions here. So you can do this on the Rubin Science platform itself, on Jupyter itself, by just git cloning this. So it'll take like a couple of seconds, and it'll create a notebook called Rubin's, a directory called Rubin CW25 anomalies. And I've organized this in one main notebook, as well as two appendix notebooks, which you might be interested in. So I'll go ahead and open up the first notebook. And a big shout out to Andres, as well as Ryan, who prepared the original anomaly detection notebooks, as well as Tatiana, who helped me do some cross matching, which we'll get to shortly. So all of this code should be runnable on the Rubin Science platform. And so let me do a one by one. So here I am essentially using some predefined filter names, colors, symbols, which are available. And the first thing I want to do is I want to query photometric data from the Rubin Science, so from the database. So I'll be choosing these features which are already there in the DIA table. So it's the flux, mean, linear slope, flux sigma, but also some other features like linear intercept, skew, chi-square, and Stetson J. So a little bit of statistics to just about. Oh, thank you. Maybe I could just, thanks for letting me know. I think that's better. I'm gonna turn this down. So yeah. Yeah, so I'm going to define the features. So these are all available in the DIA object catalog. And I'm going to query these along with the DIA object RA and DEC and just run the cell. And that should take not more than a few seconds. So yeah, I just retrieved 16,000 DIA objects, where I can also look at the table here. And you can see that I have a DIA object ID along with RA deck, as well as the other features I mentioned. So these are features that are already available, like I mentioned, and we're going to be using these features to sort of run our anomaly detection methods on. Later on at the end, I do talk about how you can use light curves directly and maybe extract features from there, but these are already available on the Rubin Science platform, on the DI object catalog, and so they're just easier to use. So this is a great starting step, but if you do want to explore further, there are other things you could do as well. And so once I have retrieved this sample, this table, I will run isolation forest on it. And so I know we've heard a bit about it till now, but just to sort of give you a rough visual representation of what an isolation forest does, is that if you have some features representing your data, it makes random cuts until it isolates a certain point. And then the main idea is that any outliers would be the ones you need the least amount of points to cut off. So that's roughly how it works. The implementation is through trees, and that's why the name random forest, and you can read more about it on scikit-learn's documentation if you want to. But this is the broad idea what it's doing. And let me use a random state, a seed basically, so that we're getting the same answers. So I'm defining an isolation forest here and fitting it to the sample, the data I queried above here. So I can do that with ifo.fit, where ifo is my isolation forest. And once you do that, you can see that it took like 1/5 of a second. You can also score the samples now, where the isolation forest determines a score, where the score is basically it's -1 if it's an extreme outlier and +1 if it's an extreme inlier. So that's what you're bound to. And then the more negative it is, the more of an outlier it is. And just to get a sense of all the scores we have on this data set we ran, we can see that how most of these range from -0.8 to -0.3-ish. And those are all the 16,000 objects. So to better look at these flagged outliers, let us maybe choose the top 20 of these. So that's what I'm doing here, choosing the top 20 most anomalous objects as per my random forest. And I can get the light curves for them. So this is done by joining the DIA object catalog with the forced source on DIA object catalog. Sorry, the DP1 visit on the forced source on DIA catalog. And you can basically get light curves for all your objects through this. And let me get the light curves for the top 20 flagged anomalies. And again, you see that I save it all in a table here. So that ran in 3.5 seconds. And I have my light curves for my 20 DIA object IDs. And so let's go ahead and plot it. And again, I have some code written here. I'm speeding a bit through this because, again, I don't want to spend a lot of time typing out. But if you plot this, you see that you can get light curves. And so going back to Alex Razim's point she made earlier, where you can see the cadence with DP1 is still much better, but it's still not as much as we would want. So you can see some of the challenges here. But you can see already that a lot of these objects, they have high amplitude values, for example. So high, sorry, not amplitude, but maximum values and so on. So ideally, then you would go about and maybe cross-match this with ZTF or maybe search for Simbad and see if any of these objects, what are these objects? So I'll leave that task up to you depending on the kind of objects you're interested in. But these are the top 20 the top 20 outliers predicted by the isolation forest. And then let me just print some details here. So in any case, let me also show you how now you can run disclassify for something similar, where this is the same animation from my slides. I told you how disclassify works, but I'm basically measuring the distance between classes as well as aggregating them across different distance metrics. And like Andres mentioned earlier, we can pip install packages as well. So you can pip install disclassify directly, but this is an older version. My anomaly detector is fairly new. So for that, I'm pip installing it directly from my GitHub repository, which has the alpha version of my code. And this also takes not too long. So you can pip install all packages, any packages you want. But in this case, I'm pip installing disclassify to run the anomaly detector method. And so let me import it. And a big difference in my method as compared to something like an isolation forest is that an isolation forest requires no labels. It gives you the points that are the most easy to isolate and returns them irrespective of what kind of classes they are. Here, I'm doing something similar to what Guillermo talked about earlier, where we want to sort of give some information about, oh, these are objects and classifications we already know, and then we want to see what's different. So for classifications, I'm cross-matching this data I queried with Gaia. I have this notebook to show you how to do that. You can run it, and it'll create this file called Gaia, and I'm going to copy it from something I prepared earlier, just so we can finish in 2 minutes. But once you have that, you can go ahead and read that in. And so you can see that Gaia has some classifications provided through its best class name column. So once I have my classifications, maybe let me just keep them in. I can see how many of these are in common with the data set I just queried earlier. And you can see that it's not a lot, but it's something. So we have 160 objects for which I do have classifications. So you can see that these are the classes I have, a lot of RRIs, AGNs, LPVs, and then a couple of some others. But that's fine. Let's still go ahead with it and run the disclassify anomaly on this. So I create my knowns as well as my known labels and features. So known labels are Y, known features are X. I create my unknown features. Now these are all 3 arrays. I instantiate my model, distance anomaly, and these are the aggregates I mentioned earlier. You can play with it. You can provide a mean and like median and things like that. Let me just stick with the default. And now it's a simple fit. And similarly, you can get the scores by just running decision function. Here, I'm negating the score I'm getting from my model directly because I want to match isolation forests definitions where a more negative number means it's more anomalous. Once I have that, very similar as above, I'm getting the more top 20 outliers, and this is the distribution of those scores, and just querying the light curves as earlier and plotting them. So that'll take like a couple of seconds, and these are the light curves. Now, again, I leave it to you to go ahead and carry on and look at these if there's anything interesting. So before I end, I just want to say that going further, ideally you would use even more features. And there are packages already out there. So Alerce has made their code public, which I've used a lot. And I have a tutorial A2, like a notebook A2, which unfortunately I wasn't able to run on the Ruben Science platform, but you can still run it to get features. But there are other packages like Lightcurve as well. And so you can use this to get a wide variety of features, then run your anomaly detector, and then still get a wide variety of features. But that is all. And please take a look and have fun with DP1, everyone. Thank you so much.
Thank you very much, everybody. We don't have any time for questions, but please find our speakers. If you have any questions for them, you can put the questions in Slack too. Thank you very much. Another round of applause for all of our speakers today.